G'day guys, we've got a microeconomics question for you today where we're asked to maximize a consumer's utility given a budget constraint. So specifically, the question is asking us to derive a generalized Marshallian demand function for an individual with Cobb Douglas utility. So let's just get through a couple of definitions first. So when this question is asking us for a generalized Marshallian demand function, this isn't for a particular number of goods. We have to be able to pull out a Marshallian demand function that can be extrapolated to an n good scenario. Okay, with Cobb Douglas utility. So basically what we have here, let me just go through some of the notation for you. So basically what we have here is we're asked to maximize this generalized utility function where we have utility is the product of a particular number of goods raised to the power of some kind of elasticity parameter. Now, the constraints also say the elasticity parameter alpha is going to be greater than 0, and we have to have constant returns to scale, i.e. all of the elasticity parameters must sum to equal 1. So what this sum of alpha I equals 1 means is that the utility experiences, the consumer's utility, experiences constant returns to scale. Great. So now just going down to our budget constraint. So we have the person's income, this is income here, is equal to the price 1 x1 plus price 2 x2. So this is the amount that we're going to spend on good 1, the amount that we're going to spend on good 2, and the amount we're going to spend on good n. So we can represent that using a summation notation, pi xi. So basically we're saying we're spending all of our income on a combination of all of these goods. And that is how we are going to be deriving our utility. So this is what we call a constrained optimization problem. So if you want to know what sort of maths this comes under, this is called constrained optimization. If you need to look at more videos, those are the videos you'll want to try and search for. Cool. So when we're doing these constrained optimization problems, what we're going to use in this particular context is what we call the method of Lagrange multipliers. Now what the method of Lagrange multipliers does is it takes our objective function, or the function that we're trying to maximize, which is utility. So this is our objective function here, and it binds it to a multiple. This is our Lagrange multiplier here. We'll just call it the Lagrange multiplier, LM. And it binds it to a multiple of our constraint here. So you can see that here's our income minus our sum of all of the goods that we buy. So it links the objective and our condition together in one function, or condition, or our boundary condition, or so it links them together in one function. Now what we want to do is we want to try and maximize the Lagrange function. Now to do that, we're going to use calculus, and more specifically what we're going to do is we're going to take first order partial derivatives of the Lagrangian function with respect to each of the goods. So what we're going to label these are our first order conditions which have to be satisfied. So these first order conditions, let's put it up here, FOC, has to be, like any optimization problem that we use differentiation for, the partial derivative of the Lagrangian function, we'll call it delta L, with respect to each of the goods that we're going to purchase has to be equal to 0. So that is a big deal in this problem. So this is our first order condition. This is what we are going to use to find our optimal consumption bundles. Okay, so let's go about taking these partial derivatives of the Lagrangian function. So I've drawn up a sort of just a reminder of basic differentiation here. I understand that a lot of people who are coming to this video might have different mathematical abilities. So just as a sort of a reminder that this is how basic differentiation works, so you can kind of tie in what I'm going to do to this Lagrangian into this basic premise of sort of the mechanics of differentiation. So let's go about taking the partial derivative of the Lagrangian with respect to our goods. So we've got delta L divided by delta xi is equal to. Now what I'm going to do is, like here, I'm going to take my power out the front of the operator. So I'm going to have alpha I times by my operator. Cool, I'm not going to write the I equals 1 and all that kind of nonsense. You guys get what that operator is. It's just this thing here. I'm going to then multiply it by xi to the alpha I. And rather than writing take 1 like we would here, I'm going to use an index law which would say that x to the negative 1 is equal to 1 over x, to then say that x to the negative 1 part of this equation will send second xi down the bottom. So using this, I can pull that xi to the alpha I minus 1 down into the denominator, and then I'm going to subtract my Lagrangian multiplier times by the price of good I. Now this, guys, has to equal, like we just said before, 0. Okay, so now we've taken our partial derivative. What I'm going to do is I'm going to, for my own sort of personal sanity and the algebra, and I guess it'll make it easier to follow, is I'm going to replace some of this with U star. Now U star is our optimum utility, and it's based on the utility function with an optimal consumption of different goods, xi. So that's what the xi star is. It's an optimal consumption of goods xi, and U star is our optimal utility. So this here is a one variable, so like it's a one number. This here is a vector of numbers. Cool. So let's go about replacing that. So what we're going to have is we're going to have just ai U star divided by xi minus, now our Lagrangian multiplier, this is now, because we've got an optimal utility, this is going to be whatever our optimal Lagrange multiplier is. This is a generalization, so we just have to say it's going to be an optimal Lagrange multiplier. Later on, you'll see that the Lagrange multiplier will cancel itself out. So it's kind of arbitrary, but for the sake of the algebra and the working, we should just take it through. So this times by the price, pi, equals 0. Cool. So we can then just rearrange this. So I'm going to take the xi over to the other side, and I'm going to equate them. I'm going to take this whole thing over to the other side, then multiply by xi. So we can just let's get rid of the 0. Let's turn this negative sign into an equals, and we're going to get rid of the fraction, multiply both sides by xi. Cool. So what I'm going to do now is I'm going to sum both sides over all of my goods that I'm going to purchase. Okay, so I'm going to sum over all of my goods, all of my prices, and all of my elasticities. The elasticities are this alpha term that is in the power in our original utility function. So as you can see, our optimal utility, U star, is not part of the sum. We're just going to sum on the left all of our elasticities, and on the right we're going to just sum all of our prices and all of our goods amounts or quantities. So the two sums that are important to us here is the sum of all of our elasticities, which will, because of our constraint, equal 1, and also you'll see that the sum of the prices times the quantities is just going to be equal to our income. So we can rewrite this then as simply U star is equal to lambda star times m. Okay guys, so now we have some optimal utility in terms of an optimal Lagrange multiplier and our income. And what we're going to do is we're going to substitute this value back into our first order condition. So we can substitute our U star in for the U star in our first order condition. So what we're going to do is we're going to put this back in here. Cool. And from what we'll be able to get from there is we'll get alpha I multiplied by lambda star m equals lambda star pi xi. Cool. So what we can also go from there is we can see that there's a lambda star on both sides. Like I said earlier, they will cancel each other out. So what we are going to get here is we're going to get alpha I times our income is equal to pi xi. Great. And the way we can interpret this sort of relationship here is that this alpha I here is the proportion of income that we spend on good xi. Okay, now what we can then do is we can find out some kind of optimal demand for xi here, because we have here a optimal value of xi to be equal to, and this is just from rearranging this formula here, alpha I times m over the price of good I. Okay, so now that we've got this optimal amount of good xi that we want to consume, or the consumer wants to buy, we can then compute the consumer's indirect utility function. So what we're going to do is we're going to substitute this relationship back into our original utility function. So what we're going to say is the person's indirect utility, which I've described up here, is a function of prices and income, is going to be equal to, so we've got our indirect utility V is equal to the operator, got like capital letter pi, multiplied by, instead of xi, we're going to write alpha I m over pi. And then we put it to the power of ai, like it has in the utility function at the top there. Okay, so we know that the income component is not going to be involved in our operator, so we can simplify our indirect utility by saying that this is equal to m times our operator, and that operator is going to be times by ai over pi to the power of alpha I. Okay, so now we've got our simplified indirect utility function. We're going to rely on an old faithful to go straight from our indirect utility function to our Marshallian demand sort of expression for our good xi. Now, the old faithful we're going to rely on is Roy's identity. So good old Roy came up with this identity that said that the Marshallian demand for any good xi can be found using the partial derivatives of the indirect utility function with respect to the price, the opposite of them, divided by the partial derivatives of the indirect utility function with respect to the person's income. So if we take the opposite of the partial derivatives with respect to price and the partial derivatives with respect to income of this indirect utility function, take the quotient of them, we can get the person's Marshallian demand. So let's go about trying to find these partial derivatives first. Okay, so let's start with the most complicated partial derivative, and that's the partial derivative with respect to price. So let's write down, we need our partial derivative of our indirect utility function with respect to the prices of all of our goods I. Cool. So what we're going to do first is we know that we've got this constant term out the front, so we can just write that in. Let's put that in, our constant term, m. Now that's going to be multiplied by our operator. So we'll just chuck the operator in. Now this is going to have to take a hike, so I'm going to run into it. Now, like our regular differentiation, the alpha I can come down the front, so we're going to have alpha I multiplied by our alpha I divided by pi, all to the power of alpha I take 1, and this then is multiplied by so we're using the chain rule here, the derivative of the inside function, which is going to be, take that up, negative ai over pi squared. So we're going to simplify this just to make our quotient easier at the end to be equal to, now m is going to stay, it'll be times by our operator of alpha I times alpha I on the price I. Now what I'm first of all going to do is break up this power here. So I'm going to then multiply that by alpha I on the price I to the power of negative 1, and then finally multiplied by negative alpha I, sorry about my handwriting, over pi squared. Great. Now what is going to happen is this will be able to flip. Okay, cool. So now that I've basically just rearranged this with that flipped, what I can do is it makes it easier to see that when I multiply these final two brackets together, that alpha I will cancel with that one, leaving negative 1. So that'll leave negative 1 up there. And this price, that'll be a 1, will cancel out with one of the prices down the bottom here. And that means that it is going to leave us with m times the operator, alpha I, times alpha I over price I to the power of alpha I, multiplied by negative 1 divided by price of I. Great. Okay, so following that, we're going to have to find our other partial derivative, which is infinitely easier to find, and that is our partial derivative of indirect utility with respect to our income. So let's have a look. We've got delta V, which is our indirect utility, over delta M, which is our income. Now, this is just going to be equal to, it's just M times this entire function is our indirect utility function, so the M will fall away, and we'll be just left with our operator times by alpha I on pi to the power of alpha I. And that is our other partial derivative. Okay, so finally we're on to our last step in our quest to find this generalized Marshallian demand function, and that is by plugging our two partial derivatives into good old Roy's identity. So we're going to have our Marshallian demand, x for a good, xi. Now, we'll label this to the power of m, which just, the uppercase M just means that it's the Marshallian demand, is going to be equal to. Now, what I'll do is I'll put in our partial derivatives, and this turns out to be negative. Now, our partial derivative with respect to price is this big thing, so we have m times our operator times alpha I ai on pi to the power of alpha I, negative 1 on pi, all divided by, we've got our partial derivative of our indirect utility with respect to income, so it's just going to be our operator times by ai over pi to the power of ai. Great. So we get out our red pen because we're going to realize that this operator and the AIs are going to all cancel out. So that and that will all cancel. So everything down the bottom is gone. So finally, our Marshallian demand, our negative at the front of Roy's identity and our -1 in our 1 over pi is going to cancel out to form a positive. And we're going to be left with AI m divided by pi. So we can see, now I'll just write this is equal to our xi, our Marshallian demand. So we can see, guys, that our Marshallian demand, our generalized Marshallian demand for any good xi is going to be related to this elasticity parameter times our income divided by the price of that particular good. Okay guys, so we've got our generalized Marshallian demand function for an individual with Cobb Douglas utility. I thought we might want to just go over quickly how we got there. So basically we identified that for an individual with Cobb Douglas utility, to get a Marshallian demand function involved constrained optimization. We had our utility function which had to be maximized, and it had to be subject to this particular income constraint. So we used Lagrange multipliers to identify what our first order conditions were, and some algebra which then ended us up with this relationship between xi, our income, price, and this elasticity constraint. We're then able to sub that into our original utility function to get an indirect utility function, which is right here. We then use good old Roy's identity to relate the indirect utility to Marshallian demand through the partial derivatives of the indirect utility function with respect to price and income. We then did a little bit more sexy algebra, and we were able to pop out with this nice, simple function which relates the good x that we're going to be demanding and the elasticity, our income, and its price. So I hope this video helped, guys. If it did, please give it a thumbs up. Subscribe to my channel. I put out new videos all the time. And if you'd like to see any videos on economics or basically anything, I'm always looking for new video ideas. But for things like this, guys, you just got to keep on keeping on. I've said it before in other videos, you just got to keep bashing your head against the wall until the wall eventually falls down. This concept didn't come to me overnight. It's taken a while for me to get my head around all of the different parameters and how they affect each other. But once you do have that eureka moment, I promise all of the effort will be worth it. So until next time, guys, just keep enjoying your economics, and I'll see you soon.